Welcome everybody to our webinar today entitled Forensic Paint Analysis with Simultaneous Submicron Optical-Photothermal Infrared, that's O-PTIR and Raman Microscopy. Our main speaker for today's talk is Associate Professor Brooke Kamrath. She's from the Forensic Science Department of the University of New Haven and quite a well-known figure in the forensic science space. I'm quite honoured to have her talking about her recent work with our Mirage instrument, and I'll be giving the introductory section of the talk just for some background purposes and some other applications examples. And my name is Dr. Mustafa Kansas. I'm the Director of Product Management and Marketing at Photothermal Spectroscopy Corp. In the interest of time, I won't read out our respective bios. I think Brooke's bio is certainly more interesting, but that can be read if you're interested from our website or from the email which you probably use to get the registration link. Now, for our attendees, you can type in your questions as you're listening into the questions box. We've also got our brochure that's available for download from the panel in front of you as well. So today's outline will basically be me talking you through the current limitations. I call these accepted limitations of FTIR microscopy. I'll probably touch a little bit about Raman as well. I'll then take you through some of the high-level principles of operation of O-PTIR. I'll take you through some examples that I think have some relevance perhaps to the forensics application space. But of course, I'll leave most of the time to Brooke in her main part of the talk. So when it comes to infrared microscopy and spectroscopy, of course, we know that infrared spectroscopy is really the study of infrared light and how it interacts with matter, and various wavelengths of infrared excite various types of vibrations between atoms in a molecule, hence giving a very characteristic signature type of spectrum, a fingerprint, if you were. And these can be applied, and infrared spectroscopy has been around for decades and decades, and it's been applied in a whole host of areas. Just a few there on your screen, but today, of course, we'll be focusing on forensics. Now, I mentioned at the start infrared microscopy limitations, and it's really FTIR microscopy, but also QCL microscopy, some of the new emerging techniques. They still have limitations when it comes to spatial resolution. So if you're using a microscope, you nearly always care about small things. But when you're working in the infrared, the typical wavelengths of the infrared spectrum that we're dealing with can be anywhere from maybe 3 microns at its shortest, but more so typically out to sort of 10, 11, 12 microns. Certainly in the fingerprint region, you're looking at sort of 6 to 12 microns of light. And there, your wavelength's going to be limited. And with various other factors come into it, in practice, you're limited to about probably 10 to 20 microns. And on the screen there, we've got a visible image of a particular target, a resolution target. And in the visible, things are relatively sharp, but take the exact same image in the infrared and things blur up significantly. Of course, because you've got longer wavelengths in the infrared compared to the visible part of the spectrum. Another key limitation is complex sample prep. Now, it's in transmission mode that for regular FTIR, that gives typically the best quality spectra. But not everything can be cut, and if it can be cut, it's often difficult to get it cut thin enough to the required thickness, which is typically 5 to 10 microns. To get around some of these, people increasingly have used micro ATR, and that's really just a germanium crystal, sometimes a diamond crystal. And this requires intimate contact with the sample, and you may not want to do that, especially if it's maybe a forensics sample, it's a delicate one-off sample. You don't want to lose it, you don't want to break it, damage it. Precise targeting can be difficult if you've got particles that you're targeting. As soon as you touch it, they can fly across the other side of the room. Of course, when you're touching things, knowing the principles of forensics, you leave something behind. There's always a risk of cross-contamination. The crystal itself can be damaged, and the sample itself can be damaged. I mean, there's an example of a typical ATR, micro ATR crystal leaving indentations as multiple spectra have been collected along its length. Perhaps a more unknown or perhaps underappreciated issue is that of dispersive, these so-called these dispersive and scatter artifacts. Now, an ideal spectrum, I think, as I said before, is measured in transmission mode. And that generates a nice looking spectrum, as you can see in the upper right hand corner here. Nice band shapes, nice flat baseline. But if you take the exact same material and make it into a bead, a 15 micron bead, the spectra looks significantly different. The peaks have split and shifted. You've got weird baseline effects, and you make it even a smaller bead, things change again, and 5 microns, they change still further. So it really goes to show that the spectra aren't just based on the chemistry, as perhaps you'd hope and want. In regular FTIR and QCL microscopy, they're also very much particle shape and size dependent, and also surface roughness dependent too. So now I've been calling these accepted limitations because that's just how it is. There's not much you can do about it. These are fundamental limitations. But a lot of those, in fact, all of those that I've mentioned there are now overcome with optical photothermal infrared. And what O-PTIR is what we consider a pump probe optical spectroscopy technique, where the pump is the infrared laser, typically a QCL, but it can also be an OPO, and the probe is a short wavelength laser, typically a 532 visible, or it could be a 785 near infrared laser as well. And with O-PTIR, we're generating submicron infrared spatial resolution rather. It's in fact very much Raman-like, but it's full of the richness of the infrared part of the spectrum. The spectra that we collect, and we typically work in reflection mode, although we can work in transmission, but reflection is the primary mode. And even when you're in reflection, the spectra that are generated are very much FTIR transmission-like. So there are no distortions, no artifacts, no interference fringes that you might get in a regular type of instrument. And it's non-contact, so that minimizes sample prep. And also the spatial resolution is infrared wavelength independent. Again, that's very much like a Raman system. So it all starts with the microscope objective. It's a reflective Cassegrain style. Through that, we shine a pulsed infrared laser beam, and being infrared, it's fairly broad, maybe around 10 microns. At the same time, we're shining in our probe beam, the green, it's about 500 nanometers. The infrared generates thermal expansion as it's expanding, and that thermal expansion changes the way the green light is reflected or scattered back. Right, so as we're tuning our infrared laser from one wavelength to the other, we monitor the intensity of the green light reflected back. And it's from that we calculate out what is essentially a pure infrared spectrum collected in reflection mode. In the next couple of slides, I'm going to take you through some key differentiators. I think it's important to stress these points because they're not always obvious. With O-PTIR, we're obtaining submicron spatial resolution in a far-field optical microscope, so it's very much like a Raman microscope in that sense. We operate in reflection mode without any of those dispersive artifacts, scattering, baseline off-cell tilts, which you might get in a regular FTIR or QCL. There's no infrared detector. Now, that might come as a bit of a shock, but it is a pump probe technique, and the probe here is a visible detector. Right, so it's a visible beam, so we use a visible detector. Right, so therefore, we use room temperature visible detectors. There's no liquid nitrogen cooling or expensive infrared detectors. No need to microtome with thin slices. We can work on thin or thick. In fact, thin can be as thin as about 100 nanometers, all the way up to as much as you can fit under the microscope, which at the moment is about 15 millimeters. We can work on glass or other visibly transparent substrates. So you don't have to work with exotic infrared transparent salt crystals. And perhaps the biggest is, because we're using a visible laser for the probe, that visible laser can also double as a Raman excitation laser. And I'll tell you more about that in a minute, but that gives us the ability to do this simultaneous infrared and Raman microspectroscopy from the same spot at the same time and with the same spatial resolution. Right, on these slides, I'm going to take you through what I think are key sort of drivers when it comes to infrared microscopy and Raman microscopy. So spatial resolution is nearly always high on people's list. I mean, if you were using a microscope, you care about small things. And if you want best spatial resolution, you're typically not going to be working with an FTIR. You'll be moving to Raman microscopy. And that's often why people use a Raman microscope, because it gives them the best spatial resolution with vibrational spectroscopy. So I've given that a green. However, Raman can suffer from fluorescence. So I've given that a red, and of course, FTIR or QCLs don't have that issue. Spectral sensitivity, Raman can be typically a low signal noise technique. That also means it's typically slower than FTIR, so we've given it a red there. When it comes to spectral interpretability, or how extensive the libraries are, given the IR side, the left-hand side, they're a green, because at least certainly for commercial libraries, you've got about a ratio of 10 to 1. So there are about 10 times as many infrared libraries as there are Raman libraries. And also just the interpretability. Typically, infrared spectra, I say typically, but generally speaking, they are much more informative and spectrally rich. If you're interested in working in a sort of far-field, non-contact mode, Raman is great for that. FTIR, well, no, you really can't work in reflection easily. Water vapor sensitivity is an issue with infrared. It's not an issue with Raman. If you're working with water as a solvent, again, IR really doesn't work with that. Raman, no issues. Glass substrates I mentioned before work fine with Raman, generally not with the infrared, and the spatial resolution dependence on wavelength. It's not with Raman, but it is very strongly dependent with infrared. So if you look at that, it's no surprise that many labs have both an infrared microscope and a Raman microscope. Depending on your experiment and your typical and your needs for that experiment, you may choose one or the other, or maybe even both. You may take your sample from one instrument to the other and get two sets of separate data. But what we do with the Mirage, and this is my favorite animation, is we literally take the best of all of those two and combine them into one instrument. And that's the O-PTIR microscopy. I've mentioned before how O-PTIR spectra are equivalent to regular FTIR spectra, and here's, I suppose, the proof in the pudding here. We've got red spectra here being the library spectra, and black is the O-PTIR spectra, so they match up virtually identically. We've got polystyrene, PET, and PMMA. Right, so very photometrically accurate across the board. Spatial resolution, you've heard me talk a lot about, and we'll probably still mention it many times throughout the talk. It is important to understand the basics and the principles of what determines spatial resolution. It's basically by the Rayleigh criterion is an easy simplification of that. And it simply says that spatial resolution is about 0.6 times your wavelength in microns divided by the numerical aperture of your objective. Now, I've taken that and plotted that using typical FTIR and QCL objectives. And if you're especially in the fingerprint region, which is the most spectrally informative part of the spectrum, your spatial resolution can be sort of upwards of 12, 13, to maybe at best sort of 6 to 7 microns. But with O-PTIR, it's flat. Not only is it extremely low, which is a good thing, you want it to be low because you want small spatial resolution around that sort of 400 nanometer mark. It's also flat. It doesn't matter whether you're at the long wavelength end or the short wavelength end, the spatial resolution is constant. Again, very much like a Raman microscope. I mentioned infrared and Raman, IR+Raman as being a big deal, and it certainly is. It's garnered a lot of interest. And the big thing here is it's same spatial resolution, so same submicron spatial resolution and the same time of measurement. Literally a 2-on-1 instrument. So it takes full advantage of the complementarity of infrared and IR. It's also confirmatory. Now, I've bolded those two words. Complementarity is something that I think we all know about, certainly those who are vibrational spectroscopists when it comes to IR and Raman, but confirmatory we need to explain that a little bit. Because it's a 2-on-1 measurement, you get two data channels with a single click of the button. You get the infrared, but you also at the same time get the Raman. So the Raman can confirm the IR result, and the IR can confirm the Raman result. Okay? We've already said it's one instrument. Certainly more thorough sample characterization than we've recently introduced a 785 probe option for those samples that are perhaps highly fluorescing on the Raman side. On that point, it is important to note that for things that are highly fluorescing in Raman, they'll still be highly fluorescing here for Raman, but they won't be highly fluorescing. In fact, they won't be fluorescing at all when it comes to the O-PTIR channel. So that is completely fluorescence free. A short applications overview, because I'm going to leave most of that to Brooke, of course. O-PTIR, much like regular FTIR, is used in an extremely wide range of application areas. IR is the workhorse of most analytical labs. And we've had, particularly with this instrument, a lot of success, especially with publications in the life science, polymeric materials, increasingly nowadays microplastics and contamination, and also failure analysis. I mentioned publications on the rise. I won't dwell on this too much. Again, in the interest of time, I will direct you to our website and publications. But it's really exciting and encouraging to see that from the introduction of the instrument, we've now gone from our starting point to, by the end of the year, I expect almost 20 publications to have come out. An application which I think has some relevance and being analogous to paint cross-sections are polymer laminates. These are often used in food packaging. So here's one that was courtesy of the IKK group and Leibniz University in Hanover. If we take a cross-section, and this is it's just a razor blade cut flat top, so it's not actually a thin section. If we take a line profile across these, and we've done 100 nanometer steps, right? That's 100 nanometer steps. So it's deliberately oversampled, and that helps. What we see is a typical nylon EVOH sandwich, and that's the spectra that are collected across that line profile. Being a QCL-based instrument from a pump probe, from a pump laser perspective, we can also tune and park the wavelengths at wavelengths of interest. In this case, I'm parking it here at, at 1641, and then we're taking the ratio of another image at 1461. And if you take the ratio, it really highlights some subtle chemical differences. In this case, we have an ultra-thin 1.6 micron layer of EVOH, right, that would be otherwise impossible to see with any other infrared instrument. Contamination on glass substrate, and I think this maybe has some relevance to forensics as well. Here's a particular glass. I think this may even be a sort of high-tech electronics type of componentry. Black or dark spot on glass. Well, the question is, what is it? And normally a measurement on glass, you wouldn't even consider it with FTIR. But over here, we can click and point and shoot on the black. We get nice organic peaks turned up, and there's still a bit of a glass background, but that can always, we can ignore those and look at the key peaks. So there's definitely more than one contaminant here, and being able to tune the laser to different wavelengths, we can also highlight where those different particles chemistries are. Here are just this is a model sample of some polystyrene. These are 900 nanometer polystyrene beads. So we've got measurements on the bead and off the bead. This happens to be on a calcium fluoride substrate. So we've got Raman data in the top. We've got O-PTIR data in the bottom. Mind you, this is from about 400 picograms of polystyrene. Right, so when you're on the substrate, of course, you've got a flat Raman baseline. When you're on the bead, you've got typical polystyrene features. The same with O-PTIR. You've got a flat baseline when you're on the calcium fluoride. When you're on the bead, you've got strong polystyrene spectra. All right, this has all been collected simultaneously. Okay, I think fibers are another interesting or useful and important trace evidence type when it comes to forensics. But fibers are typically very difficult to measure in infrared. You'd have to really squeeze them between a diamond compression cell that ends up destroying it, certainly changing the morphology of the sample. It's also quite finicky and difficult to work with. In this case, I want to show an example of a fiber that was interested. The interest here was actually fabric softener coating. So this is a fiber that's about 20 microns in diameter, and we've measured along the length of the fiber. Now again, this is in reflection mode. Doing this, so it's non-contact reflection mode. If you did this in FTIR or any QCL measurements, it just wouldn't work at all. So we get excellent looking PET spectra. These are raw spectra, mind you. This has not been corrected in any way whatsoever. So we've got strong PET spectra, and we can see some additive peaks that are changing along the length. So it goes to show that, at least in this case, the coating wasn't uniform. Right, so 20 microns is impressive to measure in reflection mode, but also measuring an 800 nanometer fiber is also pretty impressive, I think, as well. Coming toward the end here, we've got another microplastic example, and the reason why I'm showing you this is, we've got infrared and Raman spectrum, that's great, But I've now taken the infrared and Raman spectra, and I'm putting these into a search database. And so typically you'd do a search and you'd have a list of hits that would turn up, and then you do another search perhaps for the Raman, you have a separate list. So what the know-it-all package can do, and by the way, it's important to note that Wiley have now acquired the know-it-all assets of Bio-Rad, so it's now the Wiley know-it-all database and software package. So what we can now do is not only perform a simultaneous infrared Raman data measurement, we can also perform a simultaneous infrared and Raman spectral library search. And the results are then plotted, not as two separate tables, but as a 2D scatter plot. On one axis, you've got the Raman spectral hit quality index, and on the other axis, we've got the infrared spectral hit quality index, which means that the hits in the upper right-hand quadrant, those that have high IR, HQI, and high Raman HQI, are the ones that are going to be most likely the correct match. So this is the infrared. So it's only the spectrum that change. Of course, the scatter plot remains the same. All right, and this goes back to what I said before about this being a confirmatory piece technique as well. So now we've collected two data channels, and we've now used those two data channels to be searched simultaneously to make sure that the identification is as accurate as it could possibly be, which I'm sure is pretty important in a forensic context. Okay, so I'm going to wrap up and hand over to Brooke very soon, but I want to finish off by saying O-PTIR, just as an infrared instrument to begin with, takes infrared microscopy beyond these accepted and traditional limits. And it essentially combines the best of IR and Raman into a single platform. Gives you submicron resolution, it's non-contact, so there's no cross-contamination, it's point and shoot. The dispersive scatter artifacts are gone relative to regular IR, and no submicron, basically. And so IR plus Raman, so it's simultaneous submicron, IR and Raman, same spot, same time, same resolution. Okay, and with that, I'm going to hand over to the main X, that's Brooke. Brooke, over to you, please.
Thank you, Mustafa. And thank you all for attending my talk on forensic paint analysis with simultaneous optical photothermal infrared and Raman microspectroscopy. I want to start off by thanking all of my co-authors. None of this work gets done in a vacuum, and we all work together to accomplish our goals. So this talk will start with a discussion of why paint, why is it important for forensic investigations. Then we'll talk about modern forensic paint analysis and what's accomplished and what's done for that. We'll then go into some results of our analysis with O-PTIR and Raman, and end with conclusions and acknowledgements. So first, why paint? Well, to understand its value and what paint's value is in a forensic investigation, it is useful to see how paint evidence is created during a vehicular accident. This video shows a car crash in slow motion. So there were no people injured. There were a couple melons sacrificed. And in addition to showing the importance of wearing seatbelts, what you can see here is when a vehicle is impacted and the metal buckles, the paint flakes off and you get shards and little pieces of paint all over. And you could see it here in this still image. So paint is one of the most common types of traces examined in forensic laboratories. Paint is ubiquitous and has many uses, including being used for decoration or to protect a surface. Or in the case of automotive paints, it is both decorative and protective since it prevents the metal frame from rusting. Paint evidence is classified into one of four categories: automotive paint from vehicles, which is commonly submitted evidence in hit-and-run cases or other vehicular accidents. Architectural paint, which comes from houses and buildings and is commonly transferred to tools or other items during breaking and enterings and home invasions. Spray paint, which has been important evidence in a number of cases, most notably the Green River Killer case, and in artwork, where the paint may need to be analyzed in forgery cases. The picture on the right shows a vehicle that was involved in a hit-and-run accident and a paint fragment recovered on the street near the victim that was used to make the association between the accident and the vehicle in question. The variety of automotive paints is tremendous. If you've been to a large parking lot outside of a mall or a store, you'll know that there are a huge variety of paint colors. Some individuals can get very creative with their car paints, as seen in the picture on the bottom left. Also, the population of paints vary. These variations can most notably be seen by looking at different colors over time. Believe it or not, in the 1970s, one of the most popular car colors was brown. Then in the 1980s and 90s, the most popular automotive paint color was red, but over the last 20 years, it has been white. This shows some of the analysis published in Axalta's Global Automotive 2018 Color Popularity Report. It shows how the popularity of automotive paint colors varies by region. And within a given paint color, there are also variations in the specific shade, as well as whether the paint is solid or if it contains effect pigments, which can make it pearlescent or sparkly. Paints not only vary with trends, but also with advancements in paint chemistry and other technologies. Automotive paint is a complex mixture composed of 5 main components. Binders give paint its final properties, such as hardness, flexibility, and solubility. Pigments are used to provide color or other effects, such as pearlescence or reflectivity. Extenders are used primarily because pigments are expensive, so they are used for economic reasons to increase the volume of paint. Additives are substances added to the paint to provide various properties, such as UV absorbers to help protect the finish from the effects of UV radiation. And solvents are used to aid in the application of the coating and also to regulate the rate of evaporation, flow properties, and viscosity of the paint. Solvents have limited forensic value because they evaporate when the paint dries, thus is not usually present in paint evidence. Automotive paints also are applied in layers, and there are usually 3 to 4 layers in original equipment manufactured paints, or OEM paints. The top layer is a clear coat, which protects the inner layers. Then there's a color coat, and last comes the primer paints, which may have 2 different layers. Although automotive paints are mass manufactured, it is the variety of physical and chemical properties that make it valuable physical evidence. One way of assessing the evidentiary significance of an automotive paint association, which is when the question paint fragment is found to be analytically indistinguishable from a known vehicle, is through population study research. Here are 4 publications that have been done over the last 40 years or so. All have shown that 100% or greater than 99% of samples from automotive paint population studies are able to be differentiated through microscopical and vibrational spectroscopic analysis. So an analogy here is luggage tags. Everybody buys them and puts them on their luggage so you can identify them at the airport. These are mass manufactured items. And my colleague, Dr. Peter DeForest, travels a lot for work. And he has this bag tag on his luggage. Even though it's a mass manufactured item, he's never seen another. And that shows that even though a material might be mass manufactured, doesn't necessarily mean that it's common. So, modern forensic paint analysis. Well, ASTM 1610 provides the standard guide for forensic paint analysis and comparison. This includes the examination of both physical and chemical characteristics. Once a sample or samples have been obtained and determined to be sufficient for examination, the physical characteristics such as color and layer structure are determined. If possible, a physical match is attempted. So for those non-forensic science folks in the audience, a physical match is really like a jigsaw puzzle match. So you have the question fragment of paint from the road, and the known car, which you think might have been the original source of the paint. And when you put them together, you see it's a perfect physical match or jigsaw fit. If a physical match is found, there is no need to continue with additional analysis, as this demonstrates individualization or source identification. In the absence of a physical match, chemical analysis is the next step. Here, forensic paint examiners are looking to identify the binder, pigments, extender, and additives. Flowcharts for identifying each of these individual components are shown here. One thing that they all have in common is binders, pigments, and additives can all be identified using FTIR spectroscopy. And Raman is particularly useful for the identification of pigment. Paint analysis by vibrational microspectroscopy traditionally requires significant sample preparation. 3 methods are shown on the left. You can have a manual cross-section, you can make a layered carving, or microtome a thin section. A 4th option is making a thin peel, which is like taking off individual coats or layers of an onion, but you take off each individual layer of paint. On the right, we have an image as viewed through an ATR crystal. This method requires less sample prep, but it's not without its faults. Once the analysis has been done, we then need to identify the components, and this is traditionally done with manual spectral interpretation. Scott Ryland and Ed Suzuki published in 2012 a chapter in the Forensic Chemistry Handbook, which outlines a method for doing infrared spectroscopy manual interpretation. This was originally done in 1995 by Scott Ryland and was republished in the 2012 chapter. And it shows the flow chart of looking at specific peaks needed to make a binder identification. There is similar type information that's used for identifying the other components of paint. The major limitations of infrared and Raman with respect to automotive paint analysis is the limited spatial resolution, the complex sample preparation, and Raman fluorescence. Now, for the limited spatial resolution, infrared suffers from the ability to only spatially resolve 10 to 20 micron spots. And some paint layers are much thinner than that, less than 10 microns, even only a couple of microns. As a result, getting infrared spectra of these samples is nearly impossible. Not completely impossible, but very, very difficult. Complex sample preparation, as I mentioned before, to get the best infrared spectra, it requires very thin cuts, around 5 to 20 microns, to collect a quality transmission mode spectra. Now, if you're using ATR, the problems with that is it requires intimate contact. It's potentially difficult to target a specific point within the paint that you want to analyze. You risk cross-contamination if you don't clean the internal reflection element between sampling. And although not common with paint, you do have the risk of damaging your internal reflection element. For Raman spectroscopy, the main limitation is fluorescence, and this is going to be true regardless of the Raman you use. So here are some of the results of our analysis. Now this shows a blue paint sample, which we called K3. And on the left, we have an optical image with a single frequency image overlaid on the inside. And you can see how, even just looking at one peak, the 1733, you can really see the distinct layers between the different paints. On the right, you have the different spectra, one from the OPO laser and the other from the QCL laser, showing valuable spectral information that enables spectral interpretation. So I can see from this spectra that the blue is a oxythane binder, which is a newer generation urethane modified acrylic. The green is an acrylic urethane, and the red, the third layer, is an acrylic urethane with a melamine modification. So we can tell this because the main absorptions of the acrylic component are the ester carbonyl stretching absorption at 1730 wave numbers, as well as a series of CO stretching absorptions between 1300 and 900 wave numbers. Urethanes are carbamates, which has a C double bond O stretching absorption that occurs at around 1700 wave numbers. Now, some acrylic urethanes, such as the layer in red, does contain a small amount of melamine, which we could see based on the 1550 wave number broadband, which is due to the triazine ring. Variations in the relative amounts of these components will produce differences in the resulting spectra, which then could be used for comparing a known and a question sample. Now, one thing to note is that these O-PTIR spectra were collected in reflection mode, but match beautifully with the known samples or known spectra from transmission spectra. Now, the Raman spectra of these three layers is shown here. And it's not uncommon to have featureless peaks or featureless spectra for several layers, except the color coat usually has great Raman spectra as long as it doesn't fluoresce. And in this case, you can see some very well-defined peaks that enable its identification as a blue thiocyanine pigment. Another thing that O-PTIR plus Raman is able to do is look at hyperspectral imaging. Now, this shows a Raman hyperspectral image displayed at the 1520 peak. And you can see that it was chosen because it has a very high absorbance or Raman intensity at the 1526. And what this enables you to see is the distribution of pigments in this paint section. And although that's not currently utilized for comparison, in the future it might be a very good way to distinguish paints with similar chemistry from each other. This shows a second sample, which we call D1, and you can see line spectra was used for this collection. A line spectra can be collected in a couple of minutes, so it's a very rapid method to look at changes along an area. In this case, we're able to see the differences between the three different layers in this paint. And also for each component, we were able to see the spectra. So this just selected one spectra from each of those to do a comparison of. And on the bottom, we have the Raman spectra. These, I'll say that I was amazed by the signal to noise ratio and the quality of spectra that this instrument is able to obtain. This slide shows the mirage ratio images, which is able to highlight the chemical differences of the layers within a paint sample. One thing particularly interesting to me is the mixing of certain chemistries at the boundary between the two middle layers. This is only a 2-micron region and isn't seen at every wave number. It is unknown why this is happening, maybe a diffusion over time of some of the chemical components, or perhaps one of the layers hasn't fully dried prior to applying the second layer. Although not currently used in forensic interrogations of paint, this mixing of the boundary has the potential to be used for discrimination and comparison. And again, this shows a Raman hyperspectral image displayed at the 1392 wave numbers, which was the highest Raman intensity band in this spectra, and again shows the distribution of pigments within this paint. One thing that should be noted is that this paint layer is only 7.8 microns in thickness. So the information that we can obtain from this would not readily be able to be obtained by traditional infrared. However, with O-PTIR, we readily were able to get a quality infrared spectra and Raman spectra simultaneously. One question I had was if optical photothermal infrared is able to distinguish between two paints that traditionally can't be distinguished. Now, this shows two different red paints, automotive paints, that were indistinguishable by microscopy alone. We did bright field, reflected light, stereo microscopy, as well as we made thin peels and cross sections to compare the different paints. And although you might see some small differences, when we looked at it ourselves through the microscope, it wasn't enough distinction to confidently say that they could be excluded from having a common source, even though I knew they did. When we analyzed them with Raman spectroscopy, they fluoresced. The color coats didn't give us any valuable information. Now, although the two fluorescences are different, which will tell you that they are different samples, the lack of discernible peaks prevents pigment identification, and that's not exactly something I want to hang my hat on when I'm doing a comparison. So we looked at the different infrared spectra using O-PTIR, and 2 spots were collected from each layer. And this is where the differences between the two different paints really shined. And although they're all overlaid, we can see that there are significant differences between the two sets of spectra. The other thing that this paint showed, and this is just showing one of the two samples, E2, is the presence of the effect pigments. Now, effect pigments are either metal or mica flakes or polymer flakes that give an effect to an automotive paint. And you can really see the structure and size and get a lot of morphological information using the single frequency imaging. And I thought that was kind of spectacular. And this shows an overlay of those 4 different ratios that were imaged in the previous slide. Again, seeing the distribution of the effect pigments and seeing the differences between the different paint layers is quite extraordinary. Now, getting back to the O-PTIR analysis, when we looked at the color coats, which by fluorescence really didn't give us much information, you could see some real differences, particularly in the peaks at 1664 and 1645. So within that region, there's significant differences that allow them to be differentiated. And when we did a manual spectral interpretation, all 4 layers of the paint could be seen and differentiated. Now, they had the same clear coat and acrylic melamine enamel, but the color coats, the primers, and both primers were different from each other, thus indicating that even though the paints look the same, spectral analysis enabled the chemical differences to be highlighted. So in conclusion, quality infrared and Raman spectra that can be compared to those in commercial spectral databases can be obtained from automotive paint samples using the Mirage+Raman microscope. O-PTIR spectra can differentiate paints that cannot be distinguished via traditional microscopy and/or suffer from Raman fluorescence. The analysis is non-contact and requires minimal sample preparation. Only a sharp cut is needed to provide a flat surface to the paint's cross-section. Additionally, the submicron spatial resolution of O-PTIR enabled information to be obtained that couldn't be obtained through any other method. The infrared analysis of thin layers that we couldn't previously analyze were easily analyzed with the Mirage. And it also enabled visualization of the distribution of chemical components along with their layer boundaries through single frequency imaging and hyperspectral imaging. These properties have value for the comparison of question and known paint samples. I'd like to thank a number of automotive body shops in Connecticut and New York who provided samples that we used in this research. And if there are any questions, I'm happy to take them now. And if you think of any later, feel free to email me at bcamrath@newhaven.edu. Thank you.
Thank you, Brooke, for that wonderful and fascinating webinar. I've got a few questions coming in, so I'll jump straight into them right away. The first one says, the IR data only goes down to 900 wave numbers. For paint binder identification, lower wave numbers are typically required. Will this hinder the ability to ID paint components?
So that's a very good question. So the instrument we used only went to 900, but current instruments are able to go down to 800. So you'd be able to do the majority of paint identification using or binder identification in paints using Ryland's flowchart. Now, the lower wave number peaks are usually used as supplemental to just support the identification. And although they're incredibly useful, I think in the future, as instrumentation gets better and better, we're going to see that lower range get extended down. And I think this won't be a real big problem in the future. And for the research here, it didn't prevent us from making identification of the binders.
Okay, thank you. The next one on my list here is one of the criticisms of cross-sections is the potential for smearing. Can you comment on this and if you saw evidence of this?
So that's something we were very interested in, and we didn't see any evidence of that. And you could see it in these hyperspectral images or single frequency images, how the boundaries are really sharp and focused. So even though it is a concern or had been a concern when doing cross sections in the past, there doesn't seem to be any evidence of it happening, even just using a really sharp blade and cutting it. So I think that we've shown that that's not really a concern to have anymore.
Okay, I think the next one, Brooke, might be sort of directed at me, or at least I'll take this one. The question says, how do you handle fluorescing samples since using a green laser, and are other options available? So firstly, let's be very clear, whether it be in anything that I've said or Brooke has said, that the infrared side, because we can do infrared and Raman. So as far as the O-PTIR, the infrared channel, is concerned, that is entirely fluorescence free. So if you had a sample that was fluorescing like crazy in the Raman channel, your O-PTIR channel would be completely fluorescent free. However, the Raman channel, like any other Raman system, is still certainly susceptible to fluorescence. And the way which we get around any fluorescence issues for the infrared side, and I'm stressing the infrared again, is the fact that we use we detect through lock-in amplification. So the pump beam, the QCL, typically is a pulsed source, and we detect the probe beam, the green light coming back at the same rate. So it's a lock-in amplifier. So it's demodulated. So that really perfectly removes any fluorescence, but not on the Raman side. And for people who are really keen on having on minimizing the fluorescence on the Raman as well, we do also offer a 785 probe beam in place of the 532. So of course, being slightly longer wavelength, you're less susceptible to fluorescence. And though the usual trade-offs in Raman are still there when it comes to 785 versus 532, when it comes to, say, sensitivity, they do not apply on the infrared side. So going from 532 to 785 will not result in any change in sensitivity. There is slight degradation in spatial resolution since you're going to slightly longer wavelengths, but no change in sensitivity, which is again quite a change to Raman, where going to 785 you give up significant sensitivity for having less fluorescence. So that's my long-winded answer to that question. This next one, Brooke, is certainly aimed at you. Question says, how could this data be incorporated into the PDQ, whatever that is? I'm sure you'll tell me in a minute.
So the PDQ is the paint database query. It's a automotive paint database originated and housed at the Canadian Royal Mounted Police. And forensic labs can submit paint samples to them for analysis and identification of potential cars or vehicles that might have that paint structure. So it's used to create investigative leads in vehicular accidents and hit and runs. Now, PDQ, you have to still input the data or the interpretation and the type of paint for each of the layers. So because we can still do the manual spectral interpretation on O-PTIR spectra, and we can do that because O-PTIR spectra look exactly the same as transmission spectra, so there's no correction needed. It really would work seamlessly with the PDQ as it stands now. Future developments of the PDQ, I believe, are planning on creating a searchable database for analysis, and I think that we would have to that Photothermal would potentially have to work with them in terms of how exactly that would be done. But the IR spectra from O-PTIR are the same in quality and peak locations and heights, so I don't think it would be a hindrance to use that database.
Okay, thank you, Brooke. I'm keeping an eye on the clock here as well. This may have to be our last question. It says, I think it's an easy one for me, this one. Are other spectral ranges available? Absolutely. Most of the material that I showed in the first half was concentrated around the QCL, which is that sort of 1800 to 800 range. And I'm glad Brooke also showed some of the OPO data. So we've got basically two pump lasers. That's the QCL, 1800 to 800, and the OPO, which covers your high wave infrared to capture all of the OH, CH, NH bands. So that does about 3600 to 2700. So you can configure a system to have one, either, or both of those samples, of those lasers rather. And with that, I do want to wrap up. For anyone whose questions haven't been answered, we'll certainly get back to you hopefully within a few days via email. If any more questions come to mind, please email Brooke directly, and then on the email chip I provided before, or myself on the email you see on this screen. And once again, I want to thank Brooke for taking the time out of her busy schedule to sit down and tell you guys and also educate me on the value of O-PTIR IR and Raman when it comes to forensics analysis. And with that, I bid you all a goodbye, farewell, and good day. Thank you.
Thank you.